Hey, you survived the first one. Great. All right, so here come the next two examples. We're going to do example 4 first, and it's filling a conical tank. So what I want to do is that right off the bat, I'm going to pause the video, and I want you to read the problem, and I want you to see if you can dissect this information. And when we come back, you'll see what I dissected from it, and I'll explain it. All right, here we go. Pause. Okay, we're back. Now, on this one here, what I was able to find out, it says here, when water runs into a conical tank at a rate of 9 feet cubed per minute. So that's feet cubed, that got me thinking volume. So I'm going to say my volume is changing at a positive 9 feet cubed per minute, okay? Because the water is going into it, so it's rising. It's more water, more stuff is being added. That's why it's positive. So then the next one, they talk about the tank standing point down has a height of 10 feet. Notice over here, okay, I said that my height, this dashed line all the way up, is 10 feet, and that my radius is 5 feet. Okay, how fast is the water level rising when the water is 6 feet deep? Okay, so this last part, I wanted to figure out what is it asking me to find. It's asking me how fast is the water level rising. Well, I come back over here, my water level is just this part right here. It wants to know how fast this is rising. I do not know this, and this is changing. Since it's changing, I give it a variable h. And this radius is not fixed either, because as it goes up, the radius gets bigger, and as it's going down, the radius gets smaller. So I'm going to give that, because again, it's not fixed. It gets an r, or a variable, with it as well. So now I need to be able to figure out how to relate this, and obviously it's talking about volume in time. So I want to find out, recall that volume of a cone is equal to 1/3 pi r squared times h, where the radius of the cone and the height of the cone. Okay, but I just can't start, you might be going, hey, I can go ahead and take derivative volume, right? I can do dv dt right here. But then you have to be cautious. You have to start, this is where you have to have a little forward thinking. Okay, my forward thinking is saying, if I take this derivative, I'm going to have an r, a dr dt, an h, a dh dt, all mixed up inside of there. And they don't give me all that information. In fact, they want me to find dh dt, but they don't tell me what my radius is. They don't tell me what my height is. They tell me what my height is. They don't tell me what how my radius is changing. How can I put this all together? And this is where we have to go again back to geometry. You have to see, well, what do I have here? What do I have here? I have one triangle right here, and then over the top of it, I have another triangle right on top. And what I'm able to see is by angle, these are two similar triangles. Okay? Because they're two similar triangles, their sides are proportional. All right? And so what I want to do is I can say then that, well, if my first proportion is, let's see here, it'd be 10 is the same as h, and 5 is the same as r. There's my setup for my proportion. I go ahead and cross multiply, and I can go ahead and say that this is going to be the same as saying 10r is equal to 5h. All right, then this is where you got to be a little strategic, okay? A little strategic. The strategic says, well, I want to find dh dt, so I want to keep my h's. So I want to solve this equation here for r. So let's go ahead and do that. When I solve it for r, I get r is equal to 1/2 h. And now I can come up with an entirely new volume equation. My entirely new volume equation will be volume equals 1/3 pi times 1/2 h squared times h. Well, and that's going to equal, okay, after I square the 1/2, the 1/3 would be 1/12 pi h cubed. Now this is something I can start taking the derivative. 1, it's easier, okay, and 2, okay, I have the pieces. I'm not going to have an r or a dr dt to worry about. So when I go ahead and take the derivative with respect to time here, I get dv dt is equal to 1/12 pi, constant, right? Take the times 3h squared. Well, I took the derivative of h, everything with respect to time, so it's going to be times dh dt. All right. And again, I check, do I have all the variables? Now that I've taken the derivative, now I can go ahead and find out what my volume would plug in stuff that I know. So dv dt is 9 is equal to 1/12. Well, if I multiply it times 3, 1/4 pi h, which is going to be my h. What's my h? H is 6 squared times dh dt. Well, 6 squared is 36. 36 divided by 4 is 9. Divided by 9 pi on each side, I get 1 pi is equal to dh dt. And there's my answer. Now I need to make sense of it. So I'll write my answer out as saying when the water reaches a height of 6, the water level is rising at a rate of 1/pi feet per second. Woo! Good problem. So let's review. I had to know what the volume was. I also had to remember about similar triangles. Okay, if you're dealing with a triangle when you're looking at something, a problem, you're going to need to know about similar triangles and Pythagorean theorem. Those are the two big things. All right. Well, let's go on. Let's go back, and we're going to do example number 2. All right. So in example 2, I want to do the same thing. I want you to read the problem. I want you to draw a picture. And I want you to label the things that are changing with variables and label things that are staying the same with numbers and change stuff into calculus notation. All right, here we go. I'm going to pause it. Bam, here it is. So look at my picture. Notice the 500 is labeled 500 because he's 500 feet away from the launching point. That's not changing. Okay. Now notice here theta is not labeled pi over 4 because that's only for that one instant. The theta as the balloon's rising. As the balloon's going up, theta is going up. And again, my height of my balloon, it's changing, so I need to put a variable with it. Okay. And changing this last part here, how fast is the balloon rising at the moment? Well, I need to find how fast the balloon is rising, the change in h over the change in time, when theta is pi over 4, and when the angle is increasing at a rate, increasing, so d theta dt is a positive 0.14 radians per minute. Okay? So how can I possibly relate an angle with a side that's opposite and a side that's adjacent? So we have to go back to our trig stuff, right? We have to remember that tangent of theta is equal to the opposite over the hypotenuse. The opposite over the adjacent. So that's going to be my h is the opposite over 500. Well, there it is. There's my relationship. So let's go ahead and start taking the derivative of it. Okay. Before I do that, I want to go ahead and say I can rewrite this to maybe make it a little bit easier for you to see this as 1 over 500 times h. So when I take the derivative, tangent theta is going to be secant squared theta. But theta is a variable, so I need to go in there times d theta dt, which is then equal to 1 over 500 h. So 1 over 500, derivative of h is 1, but it's a variable, so dh dt. Okay. And let's go ahead and I can plug in, right? Well, no, I want to solve for dh dt. This is because it's somewhat easy. All right, so 500 secant squared theta of d theta dt is equal to dh dt. So I solved for it. now let's go ahead and plug in for the values that we do know. So this will be 500 secant squared of pi over 4 times 0.14 is equal to dh dt. Okay, so at this point you can get out your calculator, but you gotta remember that secant squared is really, okay, secant squared is, you can't do that on your calculator. So when you do this on your calculator, would be 1 over cosine of pi over 4. Okay, and then that is squared for the secant squared, that's cosine squared, okay, times 0.14 and times the 500. All right. Now you would maybe also asked to do this by hand, but the fact that they put in here that it's 0.14, that means to me it's a calculator. So when I go ahead and put this in the calculator type of a thing, I get 140 is equal to dH dt. Okay, so what does that mean? That means I gotta write my sentence out. Okay, that means you can say when, okay, the angle of elevation is pi over 4, the balloon is rising at a rate of 140. Now we got to think about units. 140. Where do they have here? Well, they talk about feet. Okay, and then in here it's radians per minute. So it's going to be feet per minute. Wow. Okay. So those are your two more examples. So things that we should get from this is we got to find any relation possible between items. Okay, when it's doing any relation possible. Okay, that could be anything from, you know, Pythagorean theorem, as we did in example 3. Okay, just simple area, as we did in example 1. Okay, trig. Okay, finally volume, and then also similar triangles, being able to use ratios. Okay, all these things that you need to be able to use. These are lots of tools, which is why this section is hard to do. So when you guys take a look at this, this is different than what was given to you at the beginning of the 6 weeks. This is the work I want you to do. Okay? Do that. Good luck. We'll talk more in the next couple of days, and we'll see you soon.